All right. We're going to talk about John Dalton. Last class with notes to introduce the ideal gas law, I remind you of Avogadro. Avogadro not only thought of 6.02 times 10 to the 23rd, but he also thought of the ideal gas law and how gases behave similar to one another. John Dalton, if you remember from Chem 1, atomic history little mini unit that we did, it kind of came up with the atomic theory, the rules that chemistry abides by. Some consider him to be the modern day father of chemistry. Dalton said if you have a mixture of gases, so no longer one gas, and that's the key to what we're going over here now. Prior to what we've been doing, we've been talking about like one gas. What happens if I change it's this or that? How many moles of this can I calculate? What's the density of that? Now we're talking about a mixture of gases. If you have a mixture of them, and they behave ideally, so in other words, remember two variables that could affect that ideal behavior. One is temperature. If you slow gases down a lot, they're more likely to interact with one another and affect one another. Secondly, if you jack up the pressure, you're squeezing them tighter together, they're more likely to disturb one another. But that's why if we're anywhere near standard temperature and pressure, they behave ideally. And if that's the case, they will act independently of one another. And what that allows us to do is come up with a couple of equations. The first one, which when I look at the equation sheet, it gives you PA, PB, PC, so I give you 1, 2, 3 instead. The total pressure of a mixture of gases is based upon the pressure of each individual gas, added up. Seems pretty simple, hopefully. Again, dot, dot, dot is saying that there could be 6, 7, 8 gases. But the key here is it doesn't matter what the gases are. They are not going to change each other's own individual pressure. Now this on its own, not that great. But this simple statement here allows us to do a little bit more complicated things. And that's what we really have to go over. I mean, I can give you a question where I give you the total pressure and the pressure of two gases and you solve for the third. That's about as minimal of a partial pressure problem as I could give you. It's harder to say partial pressure problem than it is to solve that one. But really, this first equation here is used so we can do other equations. And some of you might have saw a little bit of that next equation when you were finishing the reading guide. It involves something referred to as mole fraction, which mole fraction is this x1 that I have written down here. Mole fraction comes up with partial pressure, and if we still did colligative property math problems, which we really don't have to anymore, but if we did, it would come up there as well. Mole fraction is referring to the number of moles, so N1, of the gas that we're trying to observe, divided by the total number of moles. And what we can do, as the definition or my explanation of how to use mole fraction right below the term shows, is if we know the total pressure in a container, and we know the mole fraction of a gas, we can solve for the pressure due to that gas. And that's the equation I'm showing on the bottom here. So P1, the pressure of that first individual gas, is equal to the mole fraction times the total pressure. The good news is those last two things on that slide are both given to you on the equation sheet. Again, they use the letter A instead of the number 1 to refer to the first gas. So this is not an equation you have to memorize, but I'll tell you right now, this is the most common equation used for test versions of partial pressure. The reason why I say that term is because in the lab we have to do a whole different set of stuff, which is my next slide. So when you were doing WebAssign tonight, I bet you used P1 equals X1 times P total. What you would do again is you'd be given maybe the number of moles of 3 different gases. You add them up to get the total number of moles, and you can take part divided by total to get the mole fraction. Mole fraction, which is the X1, multiplied by the total pressure will give you the pressure due to that individual gas. You can do for all the gases. So the bottom 2 equations, those are the ones that most likely you're going to be using on WebAssign and probably on a test. Okay? We have a lab on Friday, however, and we cannot just measure the number of moles very easily, if anything. So these 2 equations in the bottom don't help us out much when it comes to lab work, which is why I need to go over another slide of how to do that with the lab. And to do that, we're going to be introducing you to a new piece of equipment called an UDIometer, which I abbreviated UDI. What we are going to be doing in the lab is we're going to fill up our tubs with water like we've done in the past. But then we're going to have a new piece of equipment. It's kind of shaped like a burette. It's a long glass tube. It has markings for volume on it, just like a burette does. It kind of reads upside down where it starts at 0 at the top, and there's an opening at the bottom. This is how we can collect a gas and then do measurements with a gas. So if I were to kind of draw this out first, and then go back to the slide to show you everything, an UDIometer works by inverting it, so having the open end down. Now again, if it's placed in a water bath, what you would do is first fill the UDIometer all the way with water. So if it is completely filled with water, then we somehow are going to get a chemical reaction to occur inside the tube. My goal is to show you this today with Alka-Seltzer, because you put Alka-Seltzer in water, it creates carbon dioxide bubbles. We collect that gas in a glass tube. We can do some math with it. We can do some calculations with it. We will actually, on Friday, be doing a reaction between magnesium metal and hydrochloric acid in that glass tube. But at some point, what happens is a reaction occurs. We collect a gas by water displacement. In other words, the gas floats up to the top of the tube, forces water out the bottom, so the water leaves, and at some point, we have a gas that's collected right here. So this would be our gas. That gas has a pressure pushing down. Again, if bubbles are created in a chemical reaction, which we can't actually create the reaction at the top, so it's going to be created at the bottom, they're going to float up due to being less dense than water. When those gases are created, they're pushing down the water. That's what's forcing it out. On the other end, there's room pressure pushing down on that. I believe on the first day that we went over gases, I kind of went over this idea of a barometer and how we can measure millimeters of mercury. It's because of that room pressure pushing down. Another thing that we have to contend with is something I call P column, the column height of water. So if we use our numbering system, I sometimes refer to this as P1. What I'm going to do is go back to the PowerPoint and show you then what I'm referring to when we label out this UDIometer setup. So, the pressure inside the UDIometer has to balance out with the room pressure. And there's 3 pressures we have to keep in mind. First is the pressure of the gas that we collect. So again, our practice session today, it's going to be Alka-Seltzer, so carbon dioxide. second one is a little more peculiar. The pressure due to water vapor. And what I mean by that, pressure is typically measured in millimeters of mercury. There's two reasons why mercury was chosen. One, it's liquid, so we need a liquid, but there's a lot of liquids out there. Water's a liquid, so why didn't we just do water instead for our unit of pressure? It's because mercury, being a metal, does not give off mercury gas phase when we collect gases with it. It's a lot more dangerous than water, so that's why we don't use it here. But because of that, whenever you collect a gas over water, not only is there going to be gas in the top part of that tube, but there's also going to be water vapor. You picked up on the way in a table that shows at any given temperature what is the pressure due to that water vapor, right? No? Am I not correct here? Oh, it was not what I expected. I'm going to hand to you a table that shows temperature and pressure. We'll notice that as you're looking at this table, as temperature increases, the pressure due to water vapor increases. Gay-Lussac's law, direct relationship between temperature and pressure. It's hotter out, the basement's usually more humid. I mean, there's a lot of examples we can go over of how pressure and temperature are related to one another. But when we're in the lab, we're going to need that little sheet of paper to tell us, okay, what's the temperature, what's the water vapor pressure. Lastly, the height of the water itself. If that water height was even with the water inside the tub, then the pressures would balance out. And there's one little hitch to this one as well. Unit of pressure could be millimeters of mercury. Again, millimeter is a distance measurement. We will be using our meter sticks to measure that column height that I showed you in the previous drawing, which I'll go back to that in a second. However, we are not measuring millimeters of mercury because we're not working with mercury in the lab. We're measuring millimeters of water. So a conversion that you need to know in order to do our lab on Friday is when you measure millimeters of water, I don't know who in the world figured this out, but if you divide your millimeters of water by 13.6, that converts it to millimeters of mercury instead. So if I go back to our picture, I have P1, a gas that we're collecting. It is pushing down here. Since I used water in my udiometer, I have water vapor in here pushing down. I have a column of water that's above the pool that it's sitting in. That's pushing down. I have three things that are pushing down, trying to get to that level. The even level between the water inside and outside the udiometer. The only thing pushing it up is the room pressure. Because when PATM is pushing down on this from all directions, the only place the water can go is up. there's a reason why the mole fraction one equation on the previous page is typically used on calculations on tests. It's because it's the easier one to go off of. This one is a little bit more complicated, although it's the one we have to use when we're working in the lab. I'm going to show you a sample problem of how we can use this information to solve a calculation. Then we're going to give you guys a little bit of time to practice this math, and then we're going to practice the technique itself to end up class as well. Again, I don't think you should write down this entire thing. That would be a little too much writing. Plus, some of the information on here we're going to be using next class. So the question I'm giving is at 780 millimeters of mercury, which by the way, that's referring to the room pressure, and 22 degrees Celsius, room temperature, you collect 30 mils of carbon dioxide. Notice that the water level in the eudiometer is 25 millimeters above the outside water level. What is the pressure of CO2? Let's think back to that drawing I just had up on the board. I had three things pushing down. Carbon dioxide gas, which was inside the eudiometer. Water vapor, which is inside the eudiometer. And the column of water that's above the level inside of the water tub itself. I have one pressure trying to push everything back up. That's the room pressure, the atmospheric pressure. Again, it says draw the setup. Well, I can just show you once again what I did for that drawing. Here's my P1, my pressure of carbon dioxide in this case. Here's my P of H2O. Again, they're both pushing down. This column, naturally, trying to fall down. So I have three things all above this green line trying to go down. The room pressure is pushing on the outside of the water bath. The only place that it can go is up. So I have that balance of those three things. That's why I set up this equality. Total pressure equal the pressure of the parts. It's just an application of the original partial pressure law of P1 plus P2 plus P3. Here's me plugging in. Room pressure, 780. PCO2, commonly what you're trying to solve for is the pressure of the gas you created. 19.84, well, that came from the water vapor table I just gave you. Look at 22 degrees Celsius, there you go. Millimeters, 25 divided by 13.6, because I have to convert this into millimeters of mercury from millimeters of water. And that's how I would get this final answer for this particular problem.